I'm Sicong from VTT, the Technical Research Center of Finland. Today, here's my topic. I will talk about the microstructural influence on gear contact fatigue. I will mostly focus on the, I will talk from the micromechanical modeling perspective. Here are my colleagues. So this work was initially motivated by the interesting project funded by the European Union. In this project, we are interested in those power transmission components. The current trend is to build bigger and more powerful wind turbines, but with longer lifetime expectancy. And bigger turbines means higher power density experienced by the critical components of the wind turbine. Locally, we will have increased contact pressure and the surface stress levels. So with those tougher operating conditions, there is a need for better tribological properties of materials. In the interesting project, our goal was to increase the load carrying capacity of gears up to 35% using the ISO standard. So we have studied the reference material is 18 chromium NEMO 76, which is commonly used for gear material in wind turbines. And during the project, we have also studied a newly developed high-strength steel, but with slightly modified chemical composition. Due to industrial confidentiality, I cannot disclose much information about the material itself, the making process especially. We have done a series of material characterization, including microstructural analysis, hardness measurement, and those mechanical property through tensile test and the impact test, but we are mostly interested in their fatigue performance. If we look at the gear, there is a rolling contact zone and the bending zone. The lifetime of the gear is limited by both. So for studying the rolling contact fatigue properties, we have this twin disc rolling test rig, so that we can adjust the slide rolling ratios by adjusting the rolling speed of those two discs, and we can apply a normal load to it. For characterizing the root bending properties, we have this pulsed type test array. Here is more details about the rolling contact fatigue test. We have this twin disc with 50 millimeter diameter, and the surface is crowned. The upper disc runs at 1,800 RPM, a lower one is slightly faster at 2,000 RPM, and the maximum load was applied here. So we have applied different normal load level from 2,000 to 1,000. As you can see in this table for both the newly developed high-strength steel and the reference steel. And to accelerate the fatigue test, because if we don't do so, that will run for years, because quite good material, I would say. So 9 indentation pits were made at the lower disc with 600 micron. And here, this picture shows the indentation after the test. And this image shows the pitting formation on the rolling contact surface of the high-strength steel. We are interested in the pitting resistant performance of these two materials. As you can see in this table, the pitting area of the high-strength steel is always higher than the reference steel under the same testing conditions. So that means the new high-strength steel shows less resistance to pitting in the rolling contact tests. And here is a test pulsed type test array we used for elaborating the ASIN curve. Here are some details about the experimental setup. We have a maximum pulsating force at 140 kilonewton for the reference steel and slightly higher for the new high-strength steel. The pulsating frequency is from 65 to 70 hertz. We have many data points here. And according to this ascent curve, we noticed that the new high-strength steel actually shows better tooth root bending fatigue property. So small summary, we have characterized these two materials through rolling contact fatigue test and tooth root bending fatigue test. It shows the new high-strength steel is less good compared to the reference steel in rolling contact fatigue test, but it outperforms the reference material during the tooth root bending fatigue test. So it raises the question, what will be the cause? We have investigated microstructure. Here, the optical image shows very similar martensitic microstructure for both. But the major difference we found is in the high-strength steel. The high-strength steel has a nearly 0% retained austenite level. And for the reference steel, we can see some very little points. This is analyzed by MTEX, the phase analysis. Those are the retained austenite phase. And if we look at the literature review, sometimes we can get very conflicting results. The majority of work suggests the softer retained austenite has a beneficial effect for fatigue properties because it's due to a lower stress level to mitigate crack propagation. But some works also suggest under high strain fatigue conditions, those strain-induced transformation of retained austenite to martensite could form a harder martensite phase, and the boundary could provide the easier path for crack propagation. Those are two schools we can see from the literatures. So to gain a more deepened understanding of the microstructural links between the macro fatigue performance and the microstructures, we have established this multi-scale modeling workflow. Firstly, macroscopic finite element models for both tooth root bending fatigue tests and twin disc rolling contact fatigue have been performed. And we extract the multi-axial loading conditions from the critical area from for this both cases and apply them to the virtual microstructure as boundary conditions. The virtual microstructure is highly representative statistically. I would say it's made from the experimental data like EBSD. And in the end, we use the crystal plasticity tool combined with this fatigue indicator parameter to evaluate which kind of microstructure could perform better. Here is shows some strain stress maps of the rolling contact finite element model, and the right side, the gear root bending model. For the rolling contact model, we have those twin disc with 2000 Newton normal force, the same rolling speed for the upper disc and lower disc. We have also made an indentation pit at the lower disc as we have used in experimental work. And the right side, to simplify the simulation, we only model the two teeth with a pulsating force from 18 to 180 kilonewton. And the location for extracting loading history is here for the gear root, and here at the below the surface, one element below surface of the twin disc. Here, this picture shows the 6 string components we extracted from the rolling contact case. We can see the actual string, the x-axis direction towards you gradually increase due to the rolling, gear rolling. We have those plasticity in the model, so we have a flattened behavior, and we also noticed the significant shear components. And for the gear root bending test, we have simulated 180 kilonewton and 140 kilonewton pulsating force. Apparently, the higher pulsating force gives higher tension strain, the X direction tension strain. And here's how we generate the statistically representative microstructures. This picture shows the EBSD orientation map. Some black lines are the reconstructed prior austenite green boundaries. And this map shows the EBSD measured orientations of greens, and you can see some small dots are those we reconstructed. In the microstructure generation, we have used the distribution of the prior austenite grain, size distribution, and also the size distribution of the retained austenite. So for in this microstructure, we have for now we have neglected the last structure. So the prior austenite grain is only divided into 4 packets using the GT orientation relationship. We have also studied, we have made a different retained austenite level from 0% to 2%, 4% until 10%. Here's a brief introduction about the crystal plasticity model I used. It's nothing special. It's a Mehigaito type crystal plasticity model. We have the slip rate, we have the kinematic hardening, isotropic hardening. We have those interaction matrix between different slip systems from the literature. And for the BCC martensitic phase, we have this 24 active slip system. And for the FCC phase, we have 12 slip system. To, as I mentioned, study the fatigue property, we have used this Fademy-Soch-like fatigue indicator parameter. As you know, the fatigue is governed by both shear components as a plane normal components. So, okay, I will go quickly. Here shows the results from the rolling contact fatigue from full martensite structure to 10% microstructure. We notice the FIP hotspots tend to gather around the green boundary, but as the increase of retained austenite volume fraction, it seems the localization has been mitigated a little bit. And here's the result from the root bending fatigue simulation. It shows very different behavior. All the FIP hotspots seems to happen in the retained austenite phase, not like the rolling contact fatigue. If we analyze the average FIP in the martensite phase, we notice that if you can see the black dot is 100% martensite phase, the 10% is below it. So that means an increase in retained austenite level could improve the fatigue resistance of the fatigue martensite phase. Similar trend we observed in the root bending fatigue tests. But here are we say two groups of curves. They are from different pulsating force level. If we analyze the FIP evaluation in the retained austenite phase, not in the martensite phase, we see that the FIP level is higher in the retained austenite phase, but grow faster on the tooth root bending fatigue from the right side image. So let me conclude. Experimentally, we have analyzed the two materials, one with 0% retained austenite level and another reference material with 2% retained austenite level. They showed different fatigue, contact fatigue properties under rolling contact fatigue and tooth root bending fatigue. We have used the crystal plasticity combined with FIP analysis to investigate the microstructural origins. The FIP, according to FIP evaluated in different phases, we found the retained austenite phase generally has an enhancing effect on the fatigue resistance of the martensite matrix. But And we also observed the distinct evolution behavior under root bending fatigue conditions. The fatigue damage accumulation significantly more localized in the RA phase. So actually, the impact of retained austenite on fatigue resistance depends on its volume fraction and the specific loading conditions in general. And some other factors we haven't done yet is the Martensite transformation because of lack of experimental evidence. We haven't done those studies at the beginning of this project, but it could be a project to explain those contradictory observations. And thank you for your attention.